We were asked to go over this question from Mastering Physics. It's called Interaction of a Current Loop with a Magnetic Field. And so we have two pictures here for this problem. And I think, well, let's maybe label these. This will be picture A, this will be picture B. And I think picture B is maybe more helpful in doing this problem. So the first thing is that there's two magnetic fields. So there's the magnetic field, I'll call it B external, EXT. That's the one that's there. It's caused by something else, maybe a solenoid, who knows? They don't tell us. Then there's the B field caused by our loop. So we got to figure out which direction the B field from our loop is pointing in. And so here the current is coming out of the page at this topper point and coming into the page here. So if I do my curly right hand rule where my fingers go with the current in the loop, if my fingers go around, then the magnetic field caused by the loop is going to point in this direction right here, sort of down here. And so this would be the B field from the loop. And so the trick here with these loops in a magnetic field is the magnetic field of the loop wants to line up with the magnetic field external. Okay, and so in this picture here, this little guy is going to want to rotate this way in what I would call a counterclockwise direction. Now, what's tricky here, and it would have been really nice if in this problem if they had labeled the angle. I think what they mean as the angle is they mean this right here, the angle between this line B and the B field external. And so in here is where they're saying this little angle theta is. That's really hard to see. And so the first question says, will the interaction of the current through the loop with the magnetic field cause the loop to rotate? It will cause it to rotate. Again, the magnetic field of the loop wants to line up with the external magnetic field, and it's going to want to go in the counterclockwise direction, like I was saying, and this will make the angle theta increase. Okay, so you got to be super careful what angle you're talking about. And then here, when we actually do our calculation, you've got to even be more super careful. So the equation we have for torque looks like this. That's the current times the area times the B field times sine of this angle. That angle is the angle between the B field. Let's see, the angle between the B field external. So let me write this in a better way. So here's B field external, and then the B field of the loop. Okay, so that's what this angle is, and that's not the angle they give you in the problem, which makes this one a little bit trickier. Okay, and so again, if this angle happens to be 0, sine of 0 is 0, and there's no torque. If the magnetic field of the loop is lined up with the external one, there is no torque. Okay, so in our problem, if we go over to here, what they're saying is they're saying that this angle here is 30 degrees. Okay, so if I draw my B field from my loop. So again, I'll differentiate B field of the loop and B field external. The angle, okay, between the B fields is actually 60 degrees. Okay, and so that's where this gets a little bit trickier. And so if I figure out this torque, if I plug in for the current, well, the current's just over here, so it's 1/2 of an amp. The area is given to you in the problem, so your numbers might be different, but my rectangle was given to me as having a side of 0.4 centimeters and then a side of 0.2 meters. Okay, so 4 centimeters and 2 centimeters is 0.4 meters and 0.02 meters. That's for the area. And then the magnetic field is given to me as 0.300 Tesla. And finally, it's sine of 60. So again, your numbers may be different here. And so when I take this, I do 1/2 times 0.04 times 0.02 times 0.3 times sine of 60. I get this number, 1.04 when I round up, times 10 to the -4 Newton meters. All right, thanks.